Today, we're going to start off with an old problem. We're going to look at a couple of functions. We're going to find the equation of a line tangent to the function at a given point. That's an important part. We know that finding the equation of a tangent line involves finding a derivative, and a derivative is a local thing. A derivative is a thing that happens at a point. When we go the other direction, when we integrate things, integration is something that happens over an interval, over a whole set. But the derivative is something happening at a point. So let's find the equation of a line tangent to a function at a given point. Let's remind ourselves of the concepts involved with the equation of the tangent line. First, we're creating the best linear approximation of a function near a point. So when we're talking about tangents, when we're talking about the equation of the tangent line is the best linear approximation of the function near the point. And by linear, we mean first degree polynomial approximation. Again, for functions that are flat at the point, we could say it'll be a 0 degree. But we're planning on a first degree polynomial. The tangent line agrees with the function in the value and in the first derivative. The tangent line has the same value and the same first derivative. So that's the big concept that we're going to be extending. The tangent line has the same value and the same first derivative. This is the concept of the tangent line. It meets the function at the same place, it intersects the function, and it's going in the same direction, same location and same direction. But those are the only two things that we're going to require. Same value and same first derivative, same location, same direction. This is how we build our best linear approximation near a point. We love this because this is the default human thinking. Whenever we average things, we're thinking linearly. Whenever we split the difference and meet in the middle, we're thinking linearly. We're drawing a line between the two places we're at, and we're just meeting in the middle of that line. This is just the default mode. Thinking ahead, because this is calculus class, we're making an approximation by making a first degree polynomial. We're going to improve our approximation by using a higher degree polynomial. We're going to calculusify this whole thing. That's a word now. That is to make more calculus-like, or to pour more calculus onto a thing. We're going to barf more calculus onto this thing. Since we improve our approximation by using more terms, calculus just says use an infinite number of terms, because that's calculus's answer to everything. Oh, you're doing a thing? Do that forever. That's the calculus way. So here is where we're going to make improvements. We improve the approximation by using more terms. Calculus here is, what's that? More terms to improve the approximation? Let's use infinitely many terms. We improve the approximation by using more terms, by matching more derivatives. Instead of just value and first derivative, our best quadratic approximation will use the same value, first derivative, and second derivative. Our best cubic approximation will use the same value, first derivative, second derivative, and third derivative. We use more terms to improve the approximation. That is, we match more derivatives. We improve the approximation by matching more derivatives. And then calculus comes along and says, do this forever. Oh, this using matching more derivatives, this is where we introduce the Taylor polynomial. Then calculus comes along and sees more terms. How about infinitely many terms? Just do that forever. And this is where the Taylor polynomial becomes a Taylor series. We just write dot plus dot 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 at the end of our Taylor polynomial. So I just keep going. And now we are playing the Taylor series game. And the Taylor series will have the form of a power series, which is the thing that we just spent the last couple of weeks thinking about. So let's find the equation of the line tangent function at a given point. There's the standard way of doing things, but there's what's running in the background that we want to highlight at this point. So our function in problem 1, our f of x is e to the x, and we're trying to think of a tangent line. We're trying to match this to a tangent line. So over in the other column, I'm going to make a tangent line called L of x. Actually, no, I'm going to name it P1 of x. I'm going to call it P1, capital P for polynomial, and 1 for first degree. The tangent line is a constant plus a linear term. A constant term plus a first degree term. So the form of my tangent line is going to be b plus mx. That's what the tangent line is. I want the value of the function and the value of this tangent line to be the same when x is 0. I want f of 0 to be the same as p1 of 0 to match the location. That's the 0th derivative. We've got our eye on Taylor series, which means Taylor polynomials, which means saying weird shit like 0th derivative. Well, let's see what that means. F of 0 is e to the 0, which is 1, and p1 of 0 is b plus m times 0, which is b. So now we've learned something. We know that the constant term of our tangent line is 1. We knew that going into this problem because we know the tangent line for e to the x near 0 is 1 plus x. But we also want the first derivative to be the same, of the function to be the same as the first derivative of our tangent line. That's the concept of the tangent line. So we want f prime of 0 to equal p1 prime of 0 to match direction. That is the first derivative. Oh, this is all happening at x equals 0. This is the concept of the tangent line. Find a line that is going through the same point as the function and is going in the same direction as the function. F prime of x is e to the x and p1 prime of x is m. I want f prime of 0, or f prime of 0 to equal p1 prime of 0. P1 prime of 0 is m, and f prime of 0 is e to the 0. So the equation of the tangent line P1 of x is 1 plus x. It's 1 plus 1x, or 1 plus x. Question. This is the same stuff that you did back in Calc 1. Calc 1, we learned about the derivative. We were practicing learning all these rules about how to find derivatives. Because it's early in the day, but late in the semester, I wanted to take it easy on myself. And so I picked the easiest derivative that still had an x in it. I also put everything near 0, so we're just plugging in 0. And so we could use our normal y equals mx plus b for our tangent line. Now we're changing things up. The next problem asks the same thing, but a different function at a different point. Now I want the equation of the line tangent to the function natural log of x at x equals 1. I couldn't do 0 again, because natural log of x is undefined at 0. So now our function g of x is the natural log of x. And I still want the equation of the line tangent to this function at x equals 1. So I'm going to write down what my line is going to look like. Now, the equation of the tangent line we used in the previous one was b plus mx. That would be trash for this situation because we're trying to find the equation of the line that goes through the point x equals 1. Why center your line? Why focus your line when x is 0, when the whole point is to look at what's going on at x equals 1? So we're going to do point slope kind of business here. I'm going to have b plus m times x minus 1. The other reason that I'm doing this is that I know that we're headed towards Taylor series, which means stopping at Taylor polynomials. Oh, actually, we're headed towards Taylor series, which means we're talking about power series. And power series always had that center. All the terms were x minus a. And so let's bring that into the equation of a tangent line. We didn't do that back in calculus because in calculus we had more pressing things on our mind than properly writing down where our lines should go. So we're putting this in terms of x minus 1 because we're going to be evaluating everything at 1. So the practical reason that we're doing things this way, we're eventually going to be upgrading to power series. And that's an important feature of our power series. So because we're finding the equation of the line tangent to the function at x equals 1, I want my equation of the line to be in terms of x equals 1. So we're going to use point slope rather than slope intercept because in this situation, we do not care about the y-intercept. Our function doesn't even have a y-intercept. So why should we be caring about some y-intercept? All right, I want g of 0 to be equal to p1 of 0. Oh, sorry, not 0. After I just talked about how much I want everything to be around 1, I write 0. I want g of 1 to be equal to p1 of 1. Because I want this all happening at x equals 1. This will get us our matching 0th derivative. So g of 1 will be natural log of 1, and I want this to equal p1 of 1. No, let's see, p1 of 1. Oops, I'm supposed to be filling it out. Clearly thinking about the future I am right now. Also, look how convenient it is for us when I plug in 1, if I center the line at 1 in the point slope form, rather than trying to mx plus b things all the time. Natural log of 1 is equal to 0. And b plus m times 1 minus 1 is equal to b. So now we have the constant term for our linear function. I also want g prime of 1 to equal p1 prime at 1 to match the first derivative. Well, g prime of x is 1 over x, and p1 prime of x is, let's see, derivative of b is 0, derivative of m times x minus 1 is m, times x minus 1 to the 0, times the derivative of the inside, which is 1. So p prime is just m. It's a first degree polynomial. Its first derivative is going to be constant. We are not surprised by this. I want g prime of 1 to equal p1 prime of 1. G prime of 1 is 1 over 1, and p1 prime of 1 is equal to m. So it looks like m should equal 1. Now we've got all the parts that we need for the equation of the tangent line. We wouldn't write it this way, except for the fact that we know that we're headed towards Taylor series. So we want things to look a little bit like power series. Really, we would write p1 of x is x minus 1. This is especially good because normally I write my constant first. Why didn't I write my constant first here? Because in this equation, I want everything to be in terms of x minus 1. So in the previous example, I wrote 1 plus x because I wrote the constant then the linear term. And here I wrote the constant then the linear term again, but now I'm being linear in x minus 1, not just plain old x. So on a multiple choice test, I would be like, which of the following is the equation of the line tangent to natural log of x at x equals 1? One of the choices would be x plus 1, x minus 1. Another choice would be negative 1 plus x. And you'd be like, oh, they're the same line. Then you look at the instructions again, and it would say, choose the best answer. This one is best. That's the really nasty thing about multiple choice tests. And the thing where most multiple choice tests, the place where multiple choice tests tend to fail. you put one right answer and four wrong answers. It should be three wrong answers, one pretty good answer, and then one answer that you intend, the best answer. And then when people argue, it's like, oh, but those are the same thing. You can say, and that view is why you lost points. Algebraically, they're the same thing, but in the context of the problem, they aren't. I would never do that. That is a very sociopathic, that would be a very sociopathic move on my part, but it would be very, very funny. Because people would lose their minds because they'd be like, oh, those are the same equations. And I would say algebraically, but this is not an algebraic problem. And people would come back to me saying, but algebraically, they're the same thing. I say that is why you're arguing from a false equivalency. All you math teachers, I'm being overly pedantic right now, so just don't at me. I'm just kidding. They can't at me. I turn comments off on my videos. Suck it, people that want to comment on my videos. Here's my email address if you want to comment on my videos. Trick question once again. I fooled you again. Bamboozled again. I don't read my email. I'm just kidding. But if I don't recognize that it's from a student, I just delete it. Incidentally, to head off some of these emails about the rightness or the wrongness, I don't have to be right in everything that I say. What has to happen is people listen to what I say and then think about whether I'm right or wrong. I'm not up here trying to be right. I'm up here trying to make people think about what they're doing and think about what they're saying. We want to get over the thing where the teacher says, George Washington had wooden teeth. And then everybody's fucking running with that as if it's true. And it's not. Here's why I think that's horrible. Wanting that kind of outcome where the teacher walks into the room and says bullshit like, George Washington had wooden teeth. Nah. and hoping that everybody just fucking believes it, that's the worst kind of authoritarianism. And I abhor that kind of bullshit. So every once in a while, I say something a little bit off. Like writing in this case, x minus 1 is correct. We're writing in the previous case, 1 plus x is better. Because now you have to fucking pay attention and think, is Leach a crazy person on this particular topic? I know I can trust him on some topics, but what if he's just a crazy person on this topic? I better find out. And not just take what I say and run with it. You're too old to be taking what anybody says and just running with it. You think about it yourself. I'm not saying do your own research, because most people that say do your own research is like, well, no. Just buy into, just look for confirmation bias. Don't do that. That's awful. Don't go out and prove yourself right. Go out and prove yourself wrong. Every day, look at the things you believe and can try to convince yourself that you are wrong about those beliefs. If you're in the position where nothing that you see will change your beliefs, you have fucked up. Decide what you will see that will change your beliefs. And then go look for it. Do you know what I mean? Don't just look for the headlines that feed you what you want to hear. That's weak. And if your beliefs don't stand up to questioning, then they aren't worth having. That's it. So in this case, I've got my function. Oh, I just wrote it out. I've got my function, f of x equals e to the x. But now, instead of a first degree polynomial, I want a second degree polynomial. And I want f of x, I want to approximate f of x equals e to the x at x equals 0. So I'm going to make, and I want a quadratic approximation, so I'm going to call it P2 of x. And I'm going to center it around x equals 0, because that's where my approximation is taking place. I'm going to use the usual A, B, C, but I'm going to write them in the order that I prefer. Constant up instead of degree down. P for polynomial, 2 for second degree. We're doing the same thing what we did before. It would be inappropriate to call it tangent parabola. That's just not a thing. But that's the idea. We're taking tangent line and just bumping it up by 1 degree into a tangent parabola. All right, so I want f of 0 to equal P2 of 0. I want f prime of 0 to be P2 prime of 0. And I want f double prime of 0 to equal P2 double prime. So I'm going to need some derivatives. F of x is e to the x, f prime of x is e to the x. F doppel prime of e to the x is e to the x. And I want these all at 0. So f of 0 to equal P2 of 0. F of 0 is going to be 1, and P2 of 0, oh, shoot. I didn't write the other side. So I also want some derivatives over here. P2 prime of x, derivative of c is 0, derivative of bx is b, and I'll have a 2a x. And I'll need the second derivative because I want to match up to here. Derivative of b is 0, the derivative of 2ax is 2a. Now I'll plug in 0 into all these places and make them equal in pairs. I want to match the first derivative. So f of 0 should equal p2 of 0. F of 0 is equal to 1. P2 of 0 is going to be c plus b times 0 plus a times 0, a square root. So 1 is equal to c. I want to match first derivative. So I want f prime of 0 to equal p2 prime of 0. So f prime of 0 is 1. P2 prime of 0 is b plus 2a times 0. So it looks like b is equal to 1. And finally, I want the second derivative to match. So f double prime of 0 should be p2 double prime at 0. P2 double prime is just constant, so 2a is equal to 1. And so that means a is equal to 1/2. And so there's the equation for our tangent parabola. That's ridiculous. We're not going to call it tangent parabola. There's the equation, or there are the coefficients in our best quadratic approximation of e to the x near x equals 0. C is a 1, B is a 1, and A is a 1/2. This quadratic function has the same value, the same first derivative, and the same second derivative at 0 that e to the x has. The other problem was g of x equals natural log of x, but this time at 1. And we want to make a tangent parabola. And we're going to focus our tangent parabola. I'm not going to use c plus bx plus ax squared. I don't want it in terms of x because my middle, the center, is not going to be 0. I want it in terms of x minus 1 because my center is at 1. I'm going to be evaluating these things at 1. So I'm going to make my life easy as far as plugging in 1 goes. I want my parabola to look like c plus b times x minus 1 plus a times x minus 1 squared. Remember, we're going to be plugging in 1. I want everything to be in terms of x minus 1 so that it's easy to plug in. We're matching derivatives, so I'm going to need some derivative. G prime of x. Derivative of natural log of x is 1 over x, or x to the negative 1. And g double prime of x is negative x to the negative 2. I'm going to need some derivatives over here in the polynomial side too, and it is unsurprising what happens here. Derivative of c is 0. The derivative of b times x minus 1 is just b. The derivative of a times x minus 1 squared is 2a times x minus 1. That's p2 prime. P2 double prime will just be 2a. No surprises here. These are the same constants that we had in the derivatives in the previous example. So I want g of 1 to equal p2 of 1. I want g of 1 to equal p2 of 1. G of 1 is natural log of 1. P2 of 1 is going to be c plus b times 1 minus 1 plus a times 1 minus 1 squared. Natural log of 1 is 0. And over here on this side, we get c. Oh, yeah. So if the values of these functions are matched, then c has to be 0. Let's match our first derivatives. I want g prime of 1 to equal p2 prime of 1. G prime of 1 is 1 to the negative 1. And p2 prime of 1 is going to be b plus 2a times 1 minus 1. 1 to the negative 1 is 1. And b plus 2a times 0 is b. Now I have the coefficient of x. And finally, I want to match second derivatives. This is the step that we have that we're going one step further. Or 1 degree higher. G double prime of 1 is negative 1 to the negative 2. And this is equal to 2a. We're at the second derivative of a quadratic, and the second derivative of a quadratic is always going to be constant. So that's why the x didn't matter here. But this tells us that a is equal to negative 1/2. We just have to divide by the 2 from the 2a. 1 to the negative 2 power is 1, and then we multiply by negative 1, negative 1/2. So p2 of x is going to be 0 plus 1 times x minus 1 minus 1/2 times x minus 1 squared. We probably wouldn't write the 0. We probably wouldn't write the 1. We write x minus 1 plus minus 1/2 times x minus 1 squared. But this is a quadratic function that has the same value as natural log of x. That 1 has the same first derivative at 1 and the same second derivative as the second derivative of natural log of x at 1. We match the value, we match the first derivative, we match the second derivative. This is the idea behind building a Taylor polynomial. Doing this forever is how we go from a Taylor polynomial to a Taylor series. Then we're looking at a power series representation for a function. And we've connected tangent lines from way back in Calc 1 to power series here in Calc 2. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day.